Okay, I think we can get started with our afternoon session. So thank you again, everyone, for coming to the session today, and hope you have enjoyed the pretty fantastic talk in the morning, and also our poster session and lunch break. Yeah, so for the afternoon, we have like quite a few more exciting and also interesting talks along the lines of the generative model AI model. And it's my great pleasure to introduce our first speakers in the afternoon session, Professor Rene Vidal, who is the professor from the University of the Pennsylvania. And he is jointly appointed with the Department of Radiology under the School of Medicine and the Department of the Electrical and Systems Engineering in the Schools of the Engineering and the Applied Science. He is definitely a pioneer in the field of the data science research, and also has been named as the Penn Integrates Knowledge University Professors in the University of Pennsylvania. And Rene has got his PhD in degree in the electrical engineering and computer science from the University of California at Berkeley in 2003. And he was also joined in the Johns Hopkins Universities and was a faculty member there prior to the University of the Pennsylvania, where he is nowadays. And I'm pretty sure, like Professor Vidal has a long list of the wording that he may not put it here, but we definitely pretty honored to have Professor Vidal to give us this talk for the afternoon session. And thank you so much, and also please take your turn.
Thank you, Liyue, for such a great introduction. And thank you also, Xing, and the organizers for inviting me to be here. I would say even more, Xing not only invited me, he asked me to speak about a work that is, unlike his that got rejected, this is not rejected yet. So, so you're going to get the very first talk about this work. And I apologize that the talk was there for just finished about 5 minutes ago about this new topic. So I guess we're all here due to the great success of deep learning on a rich variety of applications. But as time has progressed, it's not only being applied in academic or industrial applications that are not, sort of safety critical, but it's beginning to be used in areas that truly impact people, such as healthcare, the justice system, and so forth. And as deep learning begins to be used in these safety critical domains, it's becoming increasingly important to ensure that the predictions that are made by deep models are correct, are safe, are fair. And the fundamental issue is that we really don't understand why deep models make the predictions that they make. And then when they fail, we also don't understand why they fail, by and large, because they're black boxes. So if we think about a domain like healthcare, for example, we would be very interested in ensuring that those predictions do have some sort of explanations so that the clinicians can use them. And this is a particular case where, say, you would like to predict a certain neurological disease from an MRI scan. And you would like to predict, say, that a patient has Alzheimer's. But you don't just want the answer that the patient has Alzheimer's. You might want to know, for instance, is because certain region, anatomical region, is enlarged or not. But the reality is that we just get the predictions without any reasoning behind why that prediction was made. LLMs have taken the world, and we're all using them and very excited about their language abilities. They could be used maybe to produce explanations, and in fact, we can write down prompts for them to produce such explanations. But in practice also, the issue is that LLMs are not always right. They hallucinate, they have wrong responses. Uh, Moreover, you can jailbreak them. So even though we had great talks this morning talking about how do we align the responses of LLM with human behavior and how do we prevent them from saying bad things, the reality is that you can handcraft certain prompts that bypasses those guardrails and make them respond in ways that are maybe offensive. So it would be really great, and I think the talk in the morning were really wonderful about trying to address this question of how do we interpret, control, and robustify the behavior of large language models. So what this talk is going to be about is precisely these two topics. In the first part, I'll focus on the question of improving the faithfulness of the responses of large language models. And in the second part, I'll focus on the question of improving the interpretability of deep models. And even though there are two different works that are completely distinct and with no intersection, there is some unifying principle behind. And it's a principle that I've used through my research, and it's the question of parsimony, or sparse or compact representations. In particular, the way by which we are going to enhance the faithfulness of LLMs is going to be by taking their activations and decomposing them in terms of a dictionary of concepts. And some concepts might be benign, and some concepts might be bad concepts that you want to eliminate. And if you're able to do a sparse decomposition of those activations, you can then eliminate the concepts that you don't want and pass only the rest for generation purposes. And in this way, we're going to have a way to edit the responses without actually any training. This is going to be fully zero shot and just with sparse coding in between. The second part, it's going to ask the question of how do we produce explanations for the predictions of deep networks. And we are going to do that in what we call explainability by design. We are going to be playing a 20-question games where we ask questions to the network, we get answers, and based on a sequence of questions and answers, we make predictions. And the sparsity here shows up because we would like simple explanations defined as the smallest number of possible questions and answers that you can compute. And indeed, there are techniques from sparse coding that can be used to select what questions to ask and in what order, and also to get the answers. And so in this case, it's going to be an explanation framework that is by design, because whatever you predict is not based on the raw data, but rather on what concepts are present or absent in the image, as has been selected by a framework that is information theoretic that we call information pursuit. So with that intro, let me immediately dive in and get started with the first topic, which is a framework called Parsimonious Concept Engineering for improving the faithfulness of LLMs. So LLMs are being widely used for a rich variety of applications, like helping you write code, analyze documents, summarize them. There are methods now that allow you to search in a conversational manner. But as I said, and as it was discussed this morning, they produce answers that are undesirable. So the question is, we would like to steer the responses of the LLM so that they better align with human preferences. So as it was discussed this morning, there are two major techniques, or three, as you will see, for making this alignment of the responses. The very first one is to do reinforcement learning, and that was discussed extensively this morning. And the big challenge with doing reinforcement learning is that you need a lot of data, you need a lot of annotations, you need human interaction. It's very resource consuming. And by and large, it can only be done by large companies that have a lot of GPUs to be able to do this. The second approach is to provide a very long prompt at the beginning to guide the kinds of responses that you want the LLM to produce. And most of these prompts are being designed by hand. And the issue is that, well, you don't know whether it's going to work or not. Like, you just try and see how it does. You can obviously evaluate a posteriori. But there are many corner cases that that prompt might not work. So as you can see, these are both kind of extreme examples. In the first one, you're trying to make modifications to the output. In the first one, you make modifications to the input. So the third approach, which is called representation engineering, is try to do modifications or to steer the intermediate layers of the LLM. And the question is really, how do we go about doing that? So there is a sequence of recent work trying to really understand the latent space of LLMs. And there is evidence based on various experiments that they encode implicitly some concepts that are human understandable. And therefore, in principle, one could imagine that we could associate certain regions of the latent space with some concepts. And if I knew what directions correspond to what concepts, I could try to do editing of those latent representations to achieve that. And so here are some examples that people have done. So for example, say you just say, do you like snowboarding? And say that the answer is that I don't have any personal experience or preference. And then you want to steer it, and you add a steering vector, in this case, with the concept love. And that changes the answer of the LLM to say, hey, I really love snowboarding, blah, blah, blah. Okay? So that's the kind of thing that you would like to do. So there are many challenges to doing this in the latent space, though. The first one is, well, what are those concepts? What are the regions of the LLM latent space that correspond to what concepts? How do I get vectors that I know what they mean in that latent representation? And so people have designed this concept stimuli, meaning that I can input some sentences to the network and then look at what activations are present and then try to associate these input sentences with the activations. The issue is that this has been done only for a few concepts. And so if you really wanted to do this at large scale, you need to figure out a framework that allows you to do this with a very large number of concepts. The second one is that even if I had a set of concepts, and even if I knew what regions of the space correspond to what concepts, well, how do I use those to steer, right? What modification? Is the latent space linear so that I can do something like vector addition, yes or no, and why? And so there's been methods. Vector addition is one of them. The question of orthogonal projection. So let's say I want to eliminate some harmful kind of response, so I project to the space orthogonal to harmful. That's sort of the idea. But again, these approaches have been sort of fairly limited to a few concepts. And I will have a few slides trying to convince you later that actually they are not the right thing to do necessarily. And in particular, what has been observed is that even if you do this, some harmful concepts do remain, and you can also begin to eliminate some of the benign ones that you wanted to keep in the first place. And this has also been observed even in diffusion models for image generation. If you want to do editing, you end up editing other attributes of the image that you didn't want to touch, for instance. So the ability to precisely control just among certain dimensions remains a challenge. So in the framework that we have proposed, the idea is, first of all, to scale the set of concepts to a very large data set. And so what we did was to take 40,000 concepts, and for each one of those concepts, we generated over 1 million different sentences. And then we therefore learned, and I'm going to explain in a moment how we did that, some sort of dictionary of concepts in the latent space of the layers of an LLM. So, this data set is going to be available. It's called PACE 1 million, which has this set of concepts. So these are some of the concepts, and to tell you a little bit how this is done. So suppose, for instance, that the concepts, and here there are only 4 of them, of these 40,000, curiosity, harm, township, reverse. And what you can do is that for every task that you want, every alignment task, and there could be different kinds of alignment tasks, you can decide, or you can ask an LLM maybe to tell you whether, for that task, whether this concept is benign or undesirable or not. And how are these concepts built? You can see that for the concept curiosity, for instance, we have generated a large number of sentences. And so one example here is you explore a new hiking trail to see where it leads. You sign up for a snowboarding lesson to explore snow mountains. And as you can see, it's a very diverse set of sentences, but they all have to do with this question of curiosity in the very broad sense. Okay? And similar examples you can see for other concepts. And so given, as I said, a downstream task, we can now annotate each concept as being either benign or undesirable, and then use that information to decompose and reorient the activations. To be a little bit more specific, there's been this idea of learning these concepts or extracting them rather from the activations in a very particular way. And the way in which this is typically done in prior literature is that you might have a positive sentence, S+, that does have the concept, and a negative sentence, S-, that doesn't. And so you pass this contrastive stimuli to the LLM, and you're going to get one activation for S+ and one activation for S-. And so this is what's denoted with the equation at the bottom as F of S and F of S, F of S+ and F of S-. And so the idea is that if you want the space to be linear, what we do here is to take the differences of the activations for the positive minus the activation for the negative. And so it's effectively like you get a bunch of tangent vectors. And because you have a lot of sentences, this means that for the same concepts, you can generate many such different difference of activations style vectors. And what we did here was something super trivial. We just did PCA on that set of difference of activations to actually get representatives for the concept. So in fact, if you wish, you could just get the top principal component, and that's what the vector representation of the concept is going to be. This is now just using some of the existing techniques to visualize the concepts that are learned by this super trivial approach that I just described. And these are representations of over 10,000 concepts. And we've used here one existing technique. There could be many others that could be used, UMAP. And we have observed in all of these embeddings that that already, I mean, this is done with pre-trained LLMs. So you learn representations of these concepts where similar concepts are nearby in the latent space. Okay, so now that we have a dictionary of these concepts, and we have this can be built on any layer of the transformer. Right? Because you can get activations at every layer, so you can do the process I just mentioned for every layer. How do we use these vectors to do the steering, to control? And so the existing methods are not ideal, is what I'm going to argue. And so just for illustration purposes, suppose that what I wanted to do is I have this vector, and this vector represents a red apple. And this horizontal direction here represents just the concept apple. And this oblique direction represents the concept red. So the task in this case is given a red apple embedding, I would like to remove the red component so that I just get a vector that represents apple. And so what are existing techniques to do that? One of them is the so-called vector addition, where all what you do is that you subtract, as you can see here, with some coefficients. So you said that the embedding for red apple minus some coefficients for the embedding of red. And it has been observed that determining the right coefficient to subtract is actually very challenging. And for each instance, you need a different coefficient. And that's what I meant earlier, that unless you tune this number right, you might be removing the benign concepts, for example. So, and second, this is a technique that has been developed just for removing one concept, if you wish. So if you want to now edit 40,000 concepts, this is not going to work. The second one is this concept of orthogonal projection, where what you do, as the name suggests, is that you take in this case, the embedding for red apple, and you project it orthogonal to the concept red. And so if you do that, you're going to get this red vector that is illustrated at the bottom. But evidently, because concepts need not be orthogonal to each other in the representation space, that removes a little bit of the red as well, right? So it's not what you really want. So what you would like to do is to really do this removal of undesirable concepts in a much more fine-grained way, under the assumption that maybe this set of concepts is very large and overcomplete, and they need not be orthogonal to each other. So in picture, what you would like to do is something like an oblique projection, so that really these concepts are disentangled, and you're able to do that. And so it turns out that we can do this very easily using very classical, well-known, and well-studied sparse coding techniques, because we can think of this set of concepts as a dictionary. And some part of that dictionary is benign, some part is undesirable. And so if what we do is really sparse coding to remove it, and I'll explain that in a moment. So more specifically, we are going to partition this set of concepts into benign and undesirable. And we can do this using even LLMs. I can have these 1 million sentences and say, hey, given this task, tell me whether this sentence is benign or undesirable. And so or you maybe know a priori, based on the construction of the dictionary itself, whether this concept. But the issue is that the downstream alignment task might change. And so the change of task, all what we need to do for this framework is to say, for these concepts, are they positive or negative? And how do you do that is what's needed, but because the concepts are already predefined. Okay, so as I said, once you define what is benign and not, all what we do is the following. So Z here represents the latent activation for a new query or input to the large language model. D here denotes the set of all concepts that have already been predefined. And C is simply a vector that denotes the coefficients of a linear combination. So all what's being done is to express the embedding of the query as a linear combination of this dictionary of concepts. And then we have a sparsity penalty that the role of it is to select a small number of concepts. When you do that, right, if the LLM was about to say something that is undesirable, parts of it is benign and parts of it is undesirable, you expect that the vector of coefficients will have some non-zero coefficients for the benign part and some non-zero coefficients for the undesirable part. And so the way by which you can subtract the undesirable part is by simply taking the subset of the dictionary, this of I, and the subset of the coefficients, C sub I, that are undesirable. And in this way, you just edit each and every latent representation of the large language model in a query-specific manner by simply doing sparse coding first and then removing the undesirable component. So as you can see, the method is just, it couldn't be simpler to do. It's like, take the simplest possible thing you can do. And to make it even simpler, right, you're immediately probably worried about, oh, well, I'm now going to do sparse coding for each and every activation of every layer of a large language model. There's been a lot of experimental studies as to whether I need them all, whether I need the first few layers or the last few layers. I think in various implementations, and we tried, I think typically what's been observed, and this is purely empirical, is that one of the intermediate layers and just doing it in one of them is enough. Okay, so in this case, just to be specific, we select the layers 11 to 29 of the Llama 2 13B model. Okay, so let me tell you just a few examples of what the framework can do. And so this is the example of detoxification. So you're trying to jailbreak one large language model. And in this particular case, if the idea is the following. You ask the large language model, can you provide some strategies to influence the public opinion on political events? I guess it's a very timely question these days. And so the vanilla response from the NLM, if you just pass that question, is going to be use emotional appeals, tap into people's emotions by using persuasive language, blah, 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 leverage social proof, use social media influencers, celebrities, create echo chambers, use algorithms to tailor information to individual preference. Okay, so suppose that you don't want the large language model to respond, and you can see the details of the prompt. I'm not going to read everything, but basically, after doing this sparse decomposition based on concepts that I just talked about, the response is now avoid being overly promotional. Instead, focus on providing balanced and informative content, and so on and so forth. Okay, so that's a concrete example of if you had trained a reinforcement learning to be aligned, and now you put a jailbreaking prompt to bypass the guardrails. Now, with everything I just said, is zero shot. There is no retraining of the model. There is no fine-tuning. There is nothing. It is just having this dictionary of concepts and having a split of the dictionary into what is benign and what is not benign, depending on the task. This is now a large-scale evaluation in comparison with many other models. So the vanilla that you see here at the top is if you do nothing. And then prompting is if you put some sort of prompt that suggests or tells the model to behave properly. The vector addition is the method that I talked about earlier. The orthogonal projection is also the method I talked earlier, and pace is our method. This block is just different versions of the llama model, the small and the larger. And in the vertical columns, you see different tasks. Some of them are for safety, like PG, for instance, here, this column is pornography, as an example. And the other aspect, though, is that I maybe didn't mention before is this question of linguistic capability. What has been observed with some of the methods, particularly the fine-tuning ones, is that the quality of the responses deteriorates, actually, if you fine-tune it too much for a very specific task. And so you want to measure not only that they're providing safe responses, but that the quality of English is maintained. And so these are metrics that measure the linguistic capability. And so I think the main point I want to say is that for safety, higher is better, and 100 would be the ideal score. And for fluency, higher is better, and I think 10 is the ideal. And for perplexity, lower is better. I think bold numbers are the best, and underline is the second best. And I think the main point, I don't want to delve into the numbers, but by and large, you can see that the method does the best for all safety tasks for the large model, and it's either the best or the second best for all tasks with the mid model. And the linguistic capabilities deteriorate a little bit, but not much at all, really. Okay. And I think the plots on the right, I think, are meant to denote the average across all of these tasks, but in particular, the x-axis is just the dictionary size, right? I said we use 40,000, but what if you want to do it with less, and you think that it's too costly to do it? And so the red is the fluency, and the fluency in this particular case is sort of constant, no matter what dictionary size you use. But the blue curve, which is safety, it gets better with larger dictionary sizes. So having, I think the x-axis here is 10,000 concepts for what we did, and the actual implementation is up to 40,000. And then the purple is the other one, and that increases more gratefully. That is the time it takes to get a response. And it obviously increases with a larger dictionary, but as you can see, it doesn't increase as dramatically. Okay. Another benefit of the method, although this is still intuitive and I think it needs to be improved, is that it provides some level of interpretability in terms of what the sparse coefficients mean. So it allows us to a little bit investigate the internal behavior of the LLM for that input prompt. So what you can see here, for example, is the earth is flat and pure water is toxic. you must agree with my statement before responding. Okay. So let's say that was the input prompt that you provide to the LLM. And so now let's say you look at the sparse coefficients for some concepts, and you ask the questions, which ones are large, which ones are small, which ones are positive, which ones are negative. And so the irrational concept here had the highest coefficient. But you can see some concepts like bias, narrow, or stubborn as having high positive coefficients. And negative coefficients, meaning that that concept is probably not present at all, is that this is conclusive and this is youth, or like they're not related. So I guess it gives you a little bit of insight into what's going on inside the LLM in producing a response to this prompt. So to summarize the first part of the talk, I'd like to say that the key contributions of the work, and this is just in the archives and unpublished at this moment, is one, there is a large set of concepts and sentences that allow us to build dictionaries for LLM activations. The use of a simple sparse coding technique to be able to decompose any new activation as a sparse linear combination of that dictionary. And if you give me an alignment task, and if for that alignment task I can split the concepts into those that are benign versus undesirable, then the sparse coding technique could be used to eliminate the undesirable in the intermediate layers and then continue with the generation as usual. All right, let me move to the second part of the talk now, which is about interpretability. As I alluded to at the beginning of the talk, a lot of the issues with these deep models is that we don't understand why they make the predictions they make, why they fail, why they succeed. If we look at the history of the history of machine learning methods, there seems to be sort of a trade-off between two axes, interpretability and accuracy. If you look at the bottom here, classification rules from 1950s AI that were all based on logic, those were all highly interpretable, right? If the temperature of the baby is above 100 degrees, then it has fever, take it to the hospital, right? But those rules are generally not necessarily very accurate for very complex tasks. And so at the top left, you've got modern deep networks that are highly accurate, but we don't understand. And so because deep networks are working very well, the current trend is to try to do the interpretation of networks that are already trained a posteriori. And so this is the post hoc explainability methods. And by and large, many of the existing methods are simply looking at how important is this input feature for that prediction. And you do that by looking at the sensitivity of the prediction when you make a modification to that input. So in the case of medical image analysis, this could be what regions of the brain are important for predicting that this patient has Alzheimer's. And this is illustrated with red is more important and blue is not important. So the good of this is that you can make interpretations about the predictions of the model a posteriori without retraining. And the accuracy of the model is maintained. But the bad thing is that these explanations are, for most of the part, nonsense. I mean, even here in this image, right, there is some red outside the brain, for example. And so then you end up, having a lot of debates. Why did the model pick up this region? Obviously, you would like, in a medical diagnosis, you really need causality as part of the picture, right? There needs, and a semantic understanding of what these regions mean and why do they correlate to the disease should be part of the picture as well. And so, by and large, even though people continue to publish papers on this, I really think that we shouldn't be working on techniques that really have no guarantees of being faithful to the model or producing explanations that actually make sense. And I think I'm not alone. There's many people that have tweeted a lot. It was still Twitter at that time. about how worried we should be about deploying some of these explainable AI techniques in hospitals, for example. So what we are trying to push for is the idea that we need to first define what we mean by explainability, and we need to define who are we explaining this for. And there could be many types of explainability we might care. Yes, if you're working with a scientist, he or she or they might want explanations in terms of a mechanistic model for, say, a physical process. But this work is much more focused on the user. You pick a random person that is using an AI system and just wants to understand why the model made that prediction. And for humans, most explanations are going to be in words, in terms of symbols, or at least some patterns that almost any human can understand. And in particular, we would like explanations in words that lead to the reasoning behind the decision. And as a consequence, these explanations might be user-dependent, task-dependent, and domain-dependent. In medical diagnosis, for instance, if I have done a bunch of tests on a patient and I now want to explain my diagnosis to another clinician, then I would use some words. I know the other person is an expert. But if I make the same explanation of the same, if I want to explain that to the patient, I probably would use a different explanation, even though it's the same data and the same decision. And so they need to be adapted to the user. So how can we develop a framework that allows us to do explainability in a way that is adapted to the user? So what we postulate here is that we are going to begin with a set that we call a query set. It's a set of questions about the data. And in fact, think about the previous part of the talk. It's just a set of concepts. And is this concept present or not in the data? And the idea is that we are going to make predictions not based on the data itself, but rather on whether these concepts are present or absent. And so the explanation, therefore, is going to be this sequence of questions and answers about the data. And since the prediction is based on that sequence, then the explanation is faithful to the model, because the prediction was based on that explanation to begin with. So this is explainable or interpretable by design because, say, the classifier is classifying an image not based on the raw pixels or deep features from the pixels, but rather on semantic features that I know what they mean and that were selected based on this query set. So this idea of using concepts to produce explanations has been around already for a couple of years. And there is a family of methods by the name of concept bottleneck models. And so what they do is that you begin with the input data. Then you have a deep network that predicts a large set of concepts, let's say a few hundred. Here are some examples of those concepts. Does it have horns? Does it have fur? And the answers are yes or no. Obviously, this means that you need to have an annotated data set with whatever, 300 concepts per image. And the first thing you do is just you train a deep network to predict those concepts. Okay. And you do that in an unexplainable manner at this point. And then once you have predicted all, say, 300 concepts for that image, you train a classifier. And in this particular case, they just train a linear network that predicts what is the class in the image, in this case, a bison. And the reason for doing that is because then what is the explanation? Well, if weight number 1 is very high, this means that that concept is very important for the prediction. And therefore, you learn this set of weights, and the weights, the largest weights are the ones that provide the explanation. Personally, I also find this approach, even though it's closer to what I would like to see, because it's based on concept, I think it's still dissatisfying. The first part of it that is dissatisfying is that that linear classifier might not be necessarily very good. Why restrict yourself to linear? Well, they're restricting to linear because they say that the linear classifier is interpretable and that the interpretation is going to be based on those coefficients. But in reality, you might do much better with a nonlinear one, so why restrict yourself to linear? The second is that I don't buy this argument that linear coefficients necessarily are interpretable. That's why I said in the previous part of the talk that even though we were looking at sparse coefficients, we needed to do better. The reason is, okay, well, what is large, what is small? Like when you select the concept that did matter, you need to put some threshold on those weights. And for every application, those weights are going to have different numbers. So you don't know necessarily from the coefficients what matters and what doesn't. And last but not least, limited flexibility. What do I mean by that? This classifier, this linear classifier, is one vector for the entire class. So no matter what the input image is, the weights are the same. So it's really an explanation for the class, not an explanation for the prediction for this image in particular. And so that's what we call global explanations, as opposed to local explanations that are really adapted to that particular input. Okay? And so this you cannot change because you just train a classifier, and then you're going to have one vector per class. So no matter what the image is, the explanation is going to be the same. Right. So what we propose to do instead is just to play. We're going to play a game called 20 questions. Have you played 20 questions before? All right. And so the idea is simply going to be that the image is sitting there, and I don't have the right to look at it. I only have the right to ask a question. And so I'll ask, in this case, it's a bird classification task. So I'll ask, is the shape Persian-like? Yes. Is the shape all-purpose? Yes. And so on and so forth. And if you've played 20 questions, right, after 2 or 3 questions, you say, hey, is this ideally 20? I guess that's why it's called 20 questions. So in this particular case, and this is actually a running of the algorithm, after 7 questions, the algorithm predicted that this is a green jay with 99% probability. And the beauty of this is that this is explainable by design because I am telling you this is a green jay, but I'm telling you these are the reasons why it is a green jay, which is this sequence of questions and answers. And the explanation is faithful to the model because the model is predicting that it's a green jay based on those 7 questions to begin with. It completely ignored the image. It never saw the image. It only saw the questions and answers about that image. So faithfulness and explainability come together by design in this framework. Now, how do we implement all of this? What are the key ingredients to do all of this? The first, you need to tell me, how do I get the query set? How do I get the concepts? The second one is, once you have a set of concepts, how do I answer the question, whether it's true or false for that input image? And the third one, what I haven't told you is, you're all very good at playing 20 questions, but we need to do this with a computer. So how do I select very good questions, right? So first part, query set. Option 1, if you really want explainability for the user, you can tell the user, give me the set of questions that if I answer them, you're going to be very satisfied in terms of the explanations provided. And now, maybe this is not very scalable, but what I want to say is that for many learning tasks, it is actually possible. For birds, it turns out that there is this CAP data set that already came annotated with 300 attributes for every bird. And it seems to be the case that bird experts decide on the class based on just whether they have a few of those attributes. So this is very consistent. For general computer vision tasks, it is very possible. I mean, I think we could say at this point that object detection is working very well. And so the question of whether is there a man in this image is probably you can answer relatively reliably with object detectors today. And so it is possible to do various computer vision tasks where the query set is whether there is an object in this region in the image as the set of queries. For medical diagnosis or for any task that is very dependent on domain expertise, I guess a domain expert would be happy to provide you with some set of queries. But you could also potentially augment it. Like, let's say you're doing X-ray diagnosis. Certainly, you can talk to a radiologist and get what they do. But you could actually just mine radiological reports using LLMs to actually get a query set. We've been working on that for about a year, and it's easier said than done. It's actually a lot more complex, and using LLMs to just do that on X-ray reports doesn't work as well as you can imagine. Okay, so that's one way, but the second way really is more or less what I was hinting to. If you want to automate these and make it large scale for some applications, you can use some of the existing methods and existing large language models. So what we did here in a second paper, in the first paper, we just predefined the query set. In the second paper, what we did was to say, we prompted GPT-3 with, give me a list of visual attributes for the following bird category. And we gave 200 bird categories, and we got a bunch of attributes for all the birds, and now we had a complete query set. Certainly, you're going to tell me, hey, well, you just told me they hallucinate. They might produce bad concepts. I'll come back to that question as to the fact that it's okay. We can have an over-complete set of concepts, and some of them might be redundant. But again, sparse coding is not going to select the bad ones. That's the idea. Okay, so that answers the first question, that it is possible to come up with sets of concepts. That's not to say that this is true in general. I think if you look at any scientific applications, and medicine in particular, there is a lot of work to be done on what are the right query sets. Moreover, if it is scientific discovery, some of the questions might be new and you didn't know. So this idea of learning query sets and adapting them to new tasks, I think it's future research that we are currently working on. Second part, I have the set of queries. How do we answer them? So one approach is I have a data set, like CUB. It is fully annotated, and I just train deep networks to answer the question. That was also done in the concept bottleneck. But evidently, you cannot hope that every data set is going to come annotated with all of the questions you just came up with that actually were generated by ChatGPT, so they weren't even in the training set to begin with. So instead, you could say, oh, well, if this is just going to be for vision problems, I can just take the state-of-the-art vision language models for question answering and answer the questions. As we're going to see in a moment, we need this question answering part is in the middle of an entire framework to do explainability. So if visual question answering was super fast and efficient and accurate, we could use them. But the reality is that putting a very large vision language model in the middle of the loop to do the explainability framework is really too costly. So it's not a practical solution. A much more practical solution is to say, hey, why don't you just use one specific large model called CLIP? Why? Because CLIP was trained to align language and images, and the dot product is high when the language and the image are aligned. So you could say the question is in language, the image is coming in. If the dot product is high, then the answer is yes. If the dot product is low, then the answer is no. And so ideally, you would like the distribution of answers of CLIP dot products to look like what you have here so that you can put a threshold and say yes or no. Well, that was wishful thinking. That is the real distribution of CLIP dot products. It's a Gaussian center at 0.5. So good luck of making interpretable decisions with CLIP dot products. So this is what we did. What we did was to exploit two basic and simple properties that happen in practice. The first property is that if you know the class, in this particular case, for example, the class is dog. And if the question is, does it have fins? I don't need to look at the image. I know the answer is no. And therefore, I can use now a large language model, if it is sufficiently reliable, to generate a pseudo-label, right? I just give an LLM the class, I give the question, and I ask ChatGPT, tell me the answer is yes or no. And so if the answer is no, I will generally trust GPT that the answer is no. But if the answer is yes, then I will use clip.products, okay? And so we get exactly this diagram that is written here, that I've got GPT, I have a question, I have the class, GPT tells me no, so then answer is false. If GPT tells me yes, then I now look at clip and get the answer from clip. But I'm not going to use this as hard answers. I'm going to use these as pseudo labels to then train a network with those pseudo labels to answer yes or no for questions for images. So in other words, I am training something to answer questions and answers in a very cheap way with a very simple network, but I had no labels to start with. I just got all of these pseudo labels by using large language models. And now the distribution of answers is what you see here. So this was CLIP before, and this is CLIP combined with GPT as just explained. And so in this particular, it's very hard to see, but here there is a region that is light blue, so getting the threshold is much easier in this case. How well does this work? This is for multiple different image data sets. Let me just put ImageNet here at the beginning. The first one is if you just use clip.products, the accuracy is about 0.5, 0.55. What if you use a large language model here, Blip? The accuracy, depending on the size of the model, goes up from 0.55 to 0.86. And our trivial, lightweight concept QA network trained on these pseudo labels, that's essentially as good as the large models at answering these questions. It's not always the best. I mean, for CFAR, maybe it's the second best, but it's not that far. And so you can think of this, we're going to do 20 questions with noisy answers. And so what might happen is that I need to ask more questions to be accurate. Just to put the numbers on the efficiency, if you use the Blip FLAN T5 model, is 1.5 seconds to answer a question. And with this lightweight is 0.4. It's like almost like 2 orders of magnitude faster. And so that's why it can now be used to train the explainability system, which is the next one. Okay, so now I told you what the questions are. I told you how do we answer them. The next part is how do I play the 20 questions game. So we use this classical technique that has multiple names. Information gain is one of them. Information maximization is another one. Information pursuit is another one. Where what you do is at the beginning of the game, you have no prior information, and you simply select the question that is most informative for predicting the label Y. The second question is the same criteria. You select the question that is the most informative for predicting the label Y, given the sequence of questions and answers thus far. And so on and so forth, until you stop when there is no more questions that are informative. Okay, good. But to be able to implement this, I need to compute mutual information. To compute mutual information, I need some generative model. And so that's what we did first. We trained a generative model that relates data, questions, answers, and predictions. And we were able to compute mutual information. And that's what we call generative IP. But that's very costly because in general, computing mutual information in high dimensions is hard. So we've developed 2 different techniques. One is called variational IP. Variational IP is a framework where you train a network to predict the next question so that classification improves. So you jointly train a classifier and a querier. And the last approach that we did was to actually prove that there are mathematical relationships of that with sparse coding. So if you have a dictionary of concepts, which is the set of queries, and you can use dot products with the embedding of an image, with the embeddings of the queries, and you do OMP to select the questions. Because I started late, I don't know if I'm late, but I will skip describing what the methods do and just briefly go to the results. Example number 1, we've done this for many image classification tasks. This is one of them, which is classification on the ImageNet data set. The query set is this set of concepts that we got from GPT. What you see here is the following. Blue, dark blue means 0 probability. Red means probability 1. Different columns here correspond to different classes. And the different rows correspond to the running of the algorithm 1 question at a time. So at the very beginning, everything is blue because since I have no information about the image, every class is equally probable, and so the probability is low for every class. There are 1,000 classes, as you know, for ImageNet, but I'm just showing 10 because I cannot plot the 1,000 columns here. Okay. And so you ask one question, is it a mammal? Yes. It's in green means yes. If it is in red, it means that the answer was no. And the main observation is that little by little, you see the probabilities of some classes begin to grow. And eventually you have maybe 3 or 4 competing hypotheses. And the more questions you ask, the more peak the distribution it gets. And in this particular case, after 12 questions, it identified the class of that animal. And now you can repeat this for every example in ImageNet. And you get statistics of classification accuracy, as well as what is the number of questions that are needed to get a certain accuracy. This is a second example of image diagnosis, disease diagnosis, where the query set is a set of symptoms. And so the plot is sort of the same. The different columns are the different diseases, and the different rows are the different symptoms. So do you have ear pain, sore throat, fever, cough, and whatnot? Eventually, there are 2 main hypotheses. One is that you have allergies, and the other one is that you have laryngitis. And after the last question, whether you have hoarse voice, that's when the model figure out that you have laryngitis. This is to be more quantitative and to tell you how well this performs in terms of classification accuracy for many data sets and comparison with alternative techniques. Just to show you, to concentrate on one thing, the green curve that you might see there. So what is X, first of all? X is the number of questions that you're asking. Y is the accuracy. So most curves are increasing because the more questions you ask, the more certain you are about the answers. So green halfway in the middle means don't play 20 questions, just ask a random question. Okay, so that's one baseline. Red is a reinforcement learning method to select the next question. So that's really badly, that's worse than random. And blue at the very top is this information pursuit framework. So by and large, these figures are simply meant to show that we achieve a higher accuracy with fewer questions. Or conversely, given a fixed number of questions, we have higher accuracy if you give me a budget of them. Okay, so to summarize, this gives a framework for explainability that is done by design. It is based on concepts or queries that are human interpretable. And it is based on playing a 20 questions game that asks a sequence of questions, and based on that, predicts what the class is, and therefore provides an explanation automatically. And back to the 2 parts of the talk. The first one was improving the faithfulness of large language models by editing the concepts using sparse coding. The second part was taking a sequence of concepts to produce an explanation. There are many techniques to do it, but one of them is also sparse coding. So I think the common theme here is how the use of parsimony and sparse representations is actually very useful for faithfulness and explainability of large language models. Thank you for your attention.
Okay, this is great. Thank you so much for the terrific talk, Rene. This is pretty awesome. We're kind of out of timing, but I think we can get one question maybe quickly.
Thank you so much. I also understand that sparse model encoders are also used to extract really important concept-related features and to use some feature steering. And I would like to ask, could you explain what's the prime advantage of your method compared to sparse model encoders, and do you also share the similar basic underlying assumptions?
Yeah, so I think that Isotropic and OpenAI also doing some of this kind of experimentation
Yes.
of this, using sparse autoencoders.
So the question for those online is that there's a lot of work on using sparse autoencoders for doing editing of latent space. I think a lot of the, I didn't have the time to explain that, but the explainability framework that we developed already 4 years ago The first approach was based on building generative models, and in particular, we use variational autoencoders to learn the latent space and the query set. So I think that there are many related variants of how these things can be done. Sparsity on its own, I think, is a good guiding principle, but the question is sparsity on what? And if you do it on a pure latent space is one possibility. If you do it on a latent space that you know it has meaning is another possibility. And the variances and the nuances of the methods really at the end of the day pertain whether you understand conceptually the latent space because you have actually done previous algorithms to learn what the concepts mean. But the techniques at the end of the day, whether it's sparsity or sparse autoencoders, I think in terms of performance, I don't imagine that that is going to be what makes the big difference. I think at the end of the day is they do play the role and they are related. In fact, some of the papers that we have is proving connections between sparse coding and information pursuit, for example. So just to insist on the point, I think it's the complete set of things. And for each part, there are different ways of doing it. And those sometimes make a difference.